6.7 Electronegativity and Bond Polarity. Now this particular section, right off the top of your head, you might think, what does this have to do with what we were just talking about? Well, it's a nice tie-in between what we were talking about with covalent and ionic bonding and later on in another chapter when we're talking about what dissolves in what. And so right now is the perfect time to do a little bit of the explanations behind some of that. So on the surface here, our learning goal for this section is to use electronegativity to determine the polarity of a bond. But it's much more than something just like that. Now, the electronegative value of an element indicates the attraction of an atom for the shared electrons in a bond. And so if you look at this table here, as you go across the chart to fluorine, the electronegativity increases. Or if you were to start down the left-hand corner, as you go up, it increases. Or you could think of it another way. As you go down, the electronegativity decreases. Or you can think of it another way. Think of it in comparison to fluorine over here. Notice, we don't at all look at the noble gases. And the reason is because they already have their 8 valence electrons. And they don't want to share, they don't want to gain, they don't want to lose. They're just going to be there and do nothing. So, we're just talking about all the other elements here. And so, we can always just look at it in comparison, for the most part, to fluorine. And there's a reason why, but higher level chemistry will tell you why it's the most electronegative element there is. And that is the attraction for those electrons. And it has to do with its teeny tiny size and the fact that it would really like to get 8 valence electrons, so it needs 1 more. Anyway, that's beside the point. Let's just go with these numbers. So I could say, let's find the electronegative value and say, let's find which is the more electronegative element. Is it phosphorus, P here, or is it gallium? Well, of course you can look at the electronegative chart, but it's all in relationship to fluorine, which is closer to fluorine. The one that's closer to fluorine over here is going to be the more electronegative element there is. So let's go back and make sure I covered everything in that last side here. So yeah, the electronegativity is high for the nonmetals, with fluorine being the highest. And over here on the metal side, it's the lowest. All right. Well, let's talk about sharing. We had said that covalent bonds shared their electrons. Well, let's apply this in a family situation. Did you always share with your brothers and sisters equally? Or did maybe your brother or your sister want you to share but never wanted to share with you? Well, this is kind of the same concept. Even though when we're talking about sharing of electrons, we need to determine, is it equal sharing or is it unequal sharing? Because if it's unequal sharing, things will, it will cause things to happen. So first of all, if it's equal sharing, then our electrons will hang out equally around each element. However, for example, chlorine is right up there and kind of next to fluorine, so it's kind of electronegative. And so those electrons, especially the ones that are shared from hydrogen, they're going to hang out closer to chlorine, just a little bit more. So you'll notice this partially, looks like a fish sign, partially negative sign here over the chlorine, and the hydrogen has a partially positive. That means it's a partial charge of negative and a partial charge of positive. So it's not equal sharing. And in this case, it's not equal, and so they're going to call it, the term is polar. Now, we got to have it be not equal enough in order to identify it as polar. So let's figure that out. Now, A nonpolar covalent bond occurs between the nonmetals, obviously. It's equal or almost equal sharing of electrons by two of them, and it has a very small electronegative difference. So if you had a nitrogen to nitrogen, well, you look on the bonding chart. Let's go back here, nitrogen 3.0 to 3.0. Well, obviously that's 0. They're going to share it equally, considered nonpolar covalent. Well, let's look at chlorine to bromine. So here's chlorine and here's bromine. You go, well, they're not exactly the same. No, they're not. However, 0.2 difference really isn't quite enough difference to make it be polar, and we'll explain that in a little bit. So it's still considered nonpolar covalent. And ditto for hydrogen to Si. When you take the absolute value of the electronegative difference, it's 0.3, and yeah, that's a little bit more than 0.0, but it's still not enough to make a difference. So I'm hoping in your mind you're going, well then, what's enough to make a difference? Well, here we go. When the difference is 0.5 or more, it's considered polar covalent, meaning it's finally enough to make a difference. A polar covalent bond becomes more polar as the difference in electronegativity increases. So the separation of charges, like the electrons going to one side in a polar bond, is called a dipole. And so we're going to represent the positive and negative ends of the dipole by using, the lowercase Greek letter delta with a positive or negative charge. Not that we all know what Greek letters are, but so that's what that charge is. So it's the one where the electrons hang out more. The one with a greater value is the negative one. Now, an ionic bond occurs between metals and nonmetals, and they are held together by charges. Let me go back. Now, these are partial charges, whereas ionic bonds are real charges because their electrons are transferred. And so there's actually, just a second ago I said that if the difference is 0.5 or greater, it's polar covalent. Well, there gets to a point where actually by using the electronegative table that it's so polar covalent that then it turns to be ionic. Well, if you want a value, that value is around 1.8. However, usually you don't have to calculate that value for ionic bonds. You can just look. If the first one's a metal, almost always it's going to be an ionic bond. And again, why? Well, now we come back here to because it has such a large electronegative difference that one is going to steal the electron from the other. So this summarizes it. If the electronegative difference is between 0 and 0.4, it's nonpolar covalent. If it's between 0.5 and 1.8, it's polar covalent. If it's 1.9 or greater, it's ionic. Or usually if there's a metal first, then it's going to probably be ionic. So you will notice here, this table 6.14 has a nice representation. Equal sharing of electrons. The purple represents where the electrons are hanging out. If it's polar covalent, the electrons are more hanging out in this larger purple area and not so much in the pinkish or mauve color. Whereas with an ionic bond, those electrons aren't even shared unequally, they are transferred. The electron from here goes over to here. So it's going to be a stronger attraction, a stronger bond. So table 6.15 has some different bond types. Excuse my doggies for barking. I guess they want to learn about electronegativity. So let's use the electronegative difference to identify the type of bond, whether it's polar covalent, nonpolar covalent, or ionic. All right, so let's pull up your electronegative chart and let's look and see. But you know what? I'm not even going to look for a K to a nitrogen. K is a metal. That's going to have to be ionic, I betcha. Well, let's look. Okay, so K 0.8, what was the other one? To nitrogen. 0.8 to nitrogen. Okay, when we do that math, that is going to be 2.2, and yeah, that is ionic. Now then, nitrogen is 3.0 and oxygen is 3.5. So 0.5 polar covalent. Yep. Chlorine to chlorine, I don't care what its value is. If it's the same value, that difference is going to be 0. So nonpolar covalent. Hydrogen, notice where even though hydrogen is over, I'm sorry, my doggies are playing. Okay, 2.1 to hydrogen to chlorine is 3.0. So 0.9, of course that's polar covalent. Whereas a carbon to hydrogen bond, and that's what a lot of oils have in them, is 0.4 nonpolar covalent, and that is a reason why, we'll learn later why your oil and water do not mix.